Oh, good evening. I see we just have Majenko in so far, so hi Majenko. We are back on the VT240. I know I said last week we wouldn't be because I was getting a bit fed up with it, but I made some unexpected progress immediately after the stream on Friday, which was that as I was tidying up, I looked at it and I thought, well, why don't I plug the keyboard in and see if we're getting any further than we were last time, since we were seeing valid boot instructions on the logic analyzer. So I plugged the keyboard in and I turned the power switch on, and it actually started flashing status codes on the LEDs on the keyboard. Didn't get as far as doing the power on self-test OK beep, but that was definitely better than it was. So I thought, well, if it's done that with the AD15 line disconnected, which is what we did last week, to bring that line up to sensible voltages, that was obviously some sort of problem. So let's reinstate the signal and see what happens, because obviously I'd cut it, because let's switch over to the other camera, that would help. There we go. So I had previously replaced this, or socketed this chip here, that one, and the AD15 line runs up here under there, and I presumed I damaged it when I was desoldering that chip. So last week we sliced the signal AD15 under here before it reaches that chip, which was the damaged section, and that allowed the signal to reach the correct 5 volts. Yes, very good, Cobb, thank you. Hello RF, hello Cobb, and hello Purple Jelly Beans. Good to see you. So we disconnected AD15 here before we got to the area that I'd reworked, and that allowed the line to come up to the correct voltages. So obviously the next step is to reinstate the signal, because obviously my rework was bad, and I disturbed the trace as I'd done over here previously. So I put another cut in the trace above this chip to isolate it, put a bodge wire between one of the ROM chips down here because I didn't want to solder directly to the T11 socket, bodge wire from there up to the via that runs to this RAM chip here, and the problem came back. So it wasn't my dodgy rework of that AND gate that had caused the problem. It was something else, and the only other thing on that line was this DRAM chip, which is the high bit of the main memory bank. So on Saturday I desoldered that. This time I was a bit more careful, just in case it was, because obviously I'd had issues with rework, so a bit more careful, got the chip out cleanly, nicely, following my method that I'd been lecturing Shelby about and he was ignoring, but it worked very nicely. So I brought that out and everything came back to life. Well, no, it didn't come back to life. The signal came back to life. Indeed, not my fuck up, so very good to know. So signal came back to life when that chip was removed. Put the chip back in and it dies again. So obviously that chip is bad, so we can show you that actually on the... let me switch back to the main cam so that I can do this. I have found something on which to... Okay, that's not going to behave itself. One moment. So if we load that from disk... No, don't load it from disk because I've made changes. Oops. Okay, 1 second. No, it's not playing ball. But anyway, with that chip in, it fails to start up. If we pull the chip, it should, but it's not. It should start up and run code. Hello, Chloe. Actually, I asked Shelby's advice about the intro because my intro was getting cut off in the VODs, and turns out his solution is exactly as jank as the one I was thinking of using, which is just put a 5-second delay before starting the stream. Anyway, what I've forgotten to do here is actually plug the... Can you tell it's too warm in here? Let's put that camera back up here. What I've got to do is attach the dip clip. Right, so let's pop that DRAM back in. Where's it gone? There. And we're still not getting any capture. What on earth have I done wrong here? Trace while storing not refreshes. Trigger on. Aha. No, that should work. Right. Oh, splendid. Well, let's pop the DRAM out and see what happens. There is a point to this. I will get to it eventually. Right. No. Huh. Do I need to connect that ground? Well, that is definitely connected the correct way around. Oh. No. Right, we are back to... yeah, it is an awful lot of chips for a simple serial terminal, but it is a graphics and colour one. However, I suspect they used a similar number of chips even in the text-only models. I mean, the graphics processor over here does have some graphics primitive support, so maybe they use a less featured one in the text-only ones. But this down here is the text accelerator it uses, and then this is the main control logic, communications logic over here. And this is not answering the question, unfortunately, of why I am not getting a trace on the logic analyzer, which I was definitely getting last night. Let's have a look. Maybe those have pulled loose. Format address and data, they're all fine. Yep. Ground, they're good. So the status bits should run from 0 is a nit. Where's my init bit gone? That would be the problem. It is datasheet time, so we want to turn that on and pull up the datasheet for the, there we go, the T11, and find its pinout. Which I thought was there but isn't. Chapter 3 pin descriptions. This is what happens when you tidy your workspace up immediately before a stream and don't notice that you've screwed something up. So init is 18, so that is connected. That's over here. So 3 disconnected, cells, those are correct. Ready. Read strobes, write strobes, ras, cas. And we're missing, no we're not, AI naught is down there, 32 pin 6 is correct. We'll try this again. Let's just check what we've got this set to do. We've got it set to trigger on the first read. No, to address 0, that'd be why. Clear. So the first read when the chip is initialized, and then not store refreshes. So that should be what we want. There we go. So I'll just switch cameras quickly so I can move this one. So we see its initialization is all nonsense, and then there we go, it starts up with a refresh and bus operation. So that is what we were seeing last time. So that 137 at the top there is jump to immediate, so the next word is where it should be jumping, 16556, and it is jumping there, and then it carries on. Yeah, sorry, armpit shot again. Oh yeah, so last time we spent a little while at the end of the stream working through what it was capturing on the data bus and decoding the opcodes by hand, and that was an obvious nonsense because it takes ages. So what we can do is we can write an inverse assembler for it, which I thought would be a nice simple job a couple of evenings during the week, and indeed writing the inverse assembler was a couple of evenings during the week, and then it took me 3-4 days to figure out how to get it onto the logic analyzer. So if we say invasm on that, may have lost sync here. That's because I started at the wrong place, so we go back up to the first instruction there, and I should have an invasm field and I don't for some reason. Why is that? Well, it can tell it's confused. That's a good thing. I added that late last night, because this chip does actually put... It did indeed work fine off stream. You know how it goes. The top bit here in the stat column, which you can't see. Come on. The top bit there is coming off the AI0 pin, and what that is it's part of the DRAM address strobes, address bits, and in 4 or 16K mode, which the chip is running in, it indicates whether it's doing an opcode fetch or an operand fetch. So it can use that to tell whether this word is actually the opcode it should be decoding, and in this case it is, and it's not, because it thinks it's an immediate. So let's see what I've done wrong there. Address. Let's say it's don't care 0000. Store no refreshes. Why were we seeing refresh cycles run? Okay. There we go. This time it worked. So we can see it's decoding the... Sorry, let me move the camera so you can read it properly. It's decoding the jump property at the top, and then that does an MTPS, which is move to processor status, which is effectively setting the current interrupt priority. So how severe an interrupt has to happen before this code gets interrupted. We then do a move of some description, and then branch, MTPS again, bunch of moves, clear some bits. So here we're doing a clear B. There's an immediate address following it. It then has to fetch every write on the T11 is a read modify write cycle, so it has to fetch the value that is in that location, 170040, fetches it and then writes back that with the lower byte cleared. So carry on a whole bunch of stuff, and eventually we get to a point where it is doing an obvious loop. There we go. So here we're testing if the low bit is set at 171004, and then we're branching back, presumably if it isn't. So that must be some sort of initialization bit, because eventually it carries on past that address 25430, so we should see a 25432 down here eventually. There is no search feature, which is vaguely annoying. There we go. Oh, 25432. There, so that loop eventually completes. So the question is, what is this 171004? And if we turn Safari back on and have a look at the terminal technical reference, 171004 is the keyboard interface, which makes sense. The first thing it does is bring up the keyboard so that it can flash status codes at us. God, Jenny with the axe. I haven't heard that name in a long time. Evening, Phil. Sorry, I wasn't paying attention to chat there. So yeah, what would be nice would be if we could ask the thing to decode those addresses for us. And I have set some symbols up in memory, so if we ask it to do that, maybe this will work. No. Why has it not recognised 171004 there as being part of the keyboard? That looks right. 17100. Address base octal symbol view size 8, right. Well, that's disappointing. Sorry, have I left this? No, I haven't left the Safari window open, have I? But yeah, unfortunately, because there just isn't enough room on the table, the logic analyzer is behind the laptop, so I can't see the screen from unless I peer over the top, which is rather irritating. But not as irritating as this symbol feature not working when it was working absolutely fine the other day. 171004 symbol. I'll tell you what, let's change it to pattern 17100X, yeah, and then maybe it will... Right, it recognises that as being part of the keyboard. Well, the patterns should... some of the patterns are individual addresses, so all bits set makes sense, apart possibly from the very lowest bit. But a range... I mean, I thought the range would say anything between 17100 and 1710007 would show up as keyboard plus offset. And when I tried it with the memory map, which is a similar range, yeah, that's bizarre. Oh well, I guess we just won't have that working for the moment. We'll switch back to octal so it's a bit smaller. Anyway, so the long and the short of it is we have a working inverse assembler now. Well, I expected this to make sense. This is all HP's fault, and I blame HP here completely for wasting several days of my time. I wrote this inverse assembler, the bulk of it on Sunday evening, finished it up a bit on Monday, and tried to download it to the analyzer. And HP stroke Agilent stroke Keysight supply a development kit for doing this, which is a 16-bit DOS real mode executable for doing the assembly, and then a tool called IAL down for sending it down to the analyzer. And this is well known not to work on modern machines at all. I think Phil actually wrote a replacement for Windows 20 odd years ago. But people say it works in DOSBox, so I tried it in DOSBox using the same serial connection I used to talk to the analyzer. And DOSBox was having none of it, it just wouldn't talk to the serial port, and you look it up and people say, oh yeah, USB serial dongles don't work very well in DOSBox. So I wrote a Perl script because that was easiest for me, to just run the same commands by hand. And there's only one trick you have to be aware of, which is that it doesn't just send down the output from the assembler, the .r relocatable object file. It sends down a byte at the front which tells it whether to display a field that lets you set. You can resynchronize it based on different parts of the instruction word, because some CPUs you can't tell that from the status bits. So there's one byte at the front and then the file. So I wrote a Perl script to do this, and I ran it, and one line, I put documentation in it, so a few lines, but otherwise yes, one line would have been fine. So I ran that, and it chugged in it word, and it clacked the floppy disk around a bit, and then nothing happened. And I thought, well, that's odd. So I tried a few more times, and then I tried a simple hello world one, and that ran, well, downloaded okay and worked once, and then I couldn't get it to do it again. So I tried the supplied example code, in case it was something I was doing stupid with my own code, and that didn't get downloaded. I mean, it would whir the floppy disk, it would clunk around a bit, and then nothing would happen. So I tried it on a Windows machine with a hardware serial port, and as expected, IAL down doesn't run on Windows, and I couldn't find anything that would on an ancient XP embedded system. So then I grabbed, let's switch back to the main camera, then I grabbed this beast, you know it's bad when you're reaching for the Amstrad, because it has a hardware serial port on the back and it runs DOS and is of a similar vintage to the HP toolset. So I put the tools on a floppy disk, and it refused to talk to the analyzer at all. So maybe there's something wonky about either the analyzer's serial port or the Amstrad serial port, or my trusty old null modem cable, which is fully populated, so I've got no idea what's wrong there. And eventually I found out that my old Pentium 4 laptop, which has a hardware serial port, if I boot that into XP and install DOSBox on that, then IAL down does work, and it sends the file down, and the logic analyzer clicks and it whirs, and then nothing happens. And at this point I was getting angry. So I did some digging, and there are the floppy disks on this are in LIF format, not anything sensible. LIF is very simple, straightforward file system. It's basically I don't think it's even a linked list. Files have to be contiguous on the disk, etc. There are tools for working with it for Unix. Well, there are some for Linux, and they do direct floppy disk access through I/O controls. So I patched those out to run them on OS 10, and it turns out that doesn't have the ability to put a file into a LIF image, it can only pull files out of it. There's another set of programs for Unix that does have the ability to put files into a LIF image, but it doesn't support setting the file type on those files, as far as I can tell, and the file type is important for the logic analyzer to recognise it as an inverse assembler. And also the on-disk format of the file is different from the on-wire format because it has a description field at the front and there's some other stuff in there, and I have no idea what it's all about. Then I found HP's own LIF utils for DOS, put them on the Amstrad, had a look at the disk, tried to copy my file directly onto the disk, and it clicked and it whirred and nothing happened. And it turns out there wasn't sufficient room on the floppy disk for the file, and nothing gives you an error message to tell you this is why it's failing. Because the space has to be contiguous, it looked like there was enough free in the DIR listing on the Amstrad, but it just wasn't big enough space. So yeah, that was 3 days wasted because the logic analyzer doesn't have an out of disk space error message when you're sending a file over the serial port. It does if you're saving it on the analyzer, but not remote. So I was fuming. So that's twice this week the logic analyzer has annoyed me, once with that and once with this single functionality not working. Anyway, to get back to the VT240, obviously that RAM chip is the fault, because if we install it, it fails to start up. There's this one here. If we install it, it fails to start up, and if we don't install it, it tries to start up but fails anyway. because obviously you've got one whole bit of RAM, you see. Come on. Why do you not? So what we'll do is we will fit, sorry I moved the camera there, some fresh ones. Switch over to the secondary camera. So if we pop one of these in, it's the same part, just slightly slower, but I've checked the timings on the bus transactions, and it taking, I think it's about 600 nanoseconds DRAM access cycle on this machine, and this one is good for, I think it was 170, so don't know why they fitted the faster dash 4 parts. This is a dash 7, so we'll fit that carefully, and we'll hope it's not fake or anything, but the seller's reviews were good. Yeah, Cobb, it does feel like that sometimes. And where have I put there's the post? Right. Seller's reviews were good, and it was sort of one person had the actual dash 4 chip at £7.50 a pop, which I thought was a bit much. And this seller had a tube of 8 of the dash 7 parts for, how much was it? 18 quid, something like that. So not too bad. So anyway, we have a chip installed, we have a logic analyzer set to run. Let's put that back on. There and run, and we'll turn on the VT240 and see what happens. Exactly the same error on the keyboard LEDs, but I wish I had video capture from the logic analyzer. It would make life so much easier, but I haven't got around to it. Need an RGB to HDMI before I can get around to it, actually, so that is one for the future. So let's go back down. So we have the same jump. It's going to be pretty much, in fact what I'm going to do quickly is scroll up so that 0 is at the top. And capture this for posterity. Clear data. IO, print everything. And that'll take it a few moments. And then what we'll do is we'll change the trace that it starts after all this initial setup and flickering of the keyboard LEDs and so on. So we can try and work out where it's getting stuck. Let me change. What is my... There we go. If I do that, you should now be able to see what's going on. Just in time for it to finish. Absolutely splendid. That was a genius move. So if we go back down here and 512, 512. 2.43. So there's obviously a second set of loops Food is always good. There's obviously several loops going on here, so what we need to do is find out what's calling this loop. Actually, we can probably skip it entirely, can't we, by saying don't store anything between 25430 and 25422. So we can do that here. Uh, 25430. Say store if not B and outside the range. That should do it. So if we run that, we should see it just skip over all those bits. In fact, let's skip right to the end and see what's there. 512. May have lost sync. Well, that's fine. Well, that's interesting, because here we knock the camera over. The fetch bit there is 0, so why is that sitting at 0? That means it's trying to fetch an operand repeatedly, so there's a knob. Okay, that's a very interesting thing to have happened. Let's start that at 463. So we do a knob, and then we're well off into the weeds here. This is okay, so if we need a better approach here. So what's that going to be? It's going to be to trigger on the first access to 25432, I think. Oh wow, you can't. Oh yes, you can. Oh, 25432. So we want to trigger on, trigger on a bus operation to that address. And we'll try that again. Okay, so that's the end of the first iteration of that loop. And it immediately gets confused. Oh, I'll tell you what's happening. No, if that's a knob, it should be absolutely fine. Let's undo that change. So not B is just skipping memory refreshes because we don't really care about those. Right, I'm obviously skipping a state that it considers vital to the disassembly, so let's pay slightly closer attention to this. 25432. Two 25420 is the knob, and then that's why I think. So if we want to skip everything between 20, 22, 46, 30. It should have been okay. Let's turn count states on so we can see how many are getting skipped, or how many memory reads are getting skipped. There we go, that's more like it. And what we can do is change that to states. No, may have lost sync again. So this column here is now telling us how many operations it's skipping over during the trace. Well, I mean, Cobb, the problem is I'm not getting very far. So I could be on entirely the wrong path here. I mean, even the debugging fluid isn't helping. What I really need is a disassembly of the ROM, I suppose, so I can figure out where these addresses are, but let's undo that. Obviously we need to be a bit more precise in our skipping over of states. Actually, why don't we go back the other way and see what calls that routine, because it's presumably a routine. There's the initial jump, so we should be able to turn the assembler off and on again. No. Yeah, drink is definitely appealing at this point. What time is it? It's coming on 10 to. We don't have a Shelby stream this evening. He is. Well, he says he was worried about rain. A rainstorm coming in and disrupting his LTE, which, to be fair, it does occasionally, but we all know he's just using an excuse to go and frolic in the rain. I get the feeling rain to Shelby is like snow to me. I'm always here for snow because it doesn't happen very often. So let's have a look. Keep scrolling and see if we can find out where this routine gets called and skip over it entirely. Now there is a... Right, these clears to 171006, I believe, are setting up the memory map. 171 is the keyboard. Okay. Keyboard is literally the first thing to get done. So, what do? We jump into it. 25508 is probably... The machine is going to get really fed up with me soon. 25508. Oh, it can't be 08, idiot, it's octal, 10. 25, yeah, so that was where we were jumping. So let's run that. No, that's not peripheral space. There we go, 170014. Right, 170014 at the top there is setting up the memory map. So that's okay. RTS R5 may have lost sync. Why? Oh, because an RTS is going to pop the stack. Okay, that's fair enough. And now we're testing 170010, which is part of the memory mapping logic. That's all exciting, isn't it? What we're ideally looking for is at some point it just might descend into an infinite loop because it's failed, and then we can work back from there. Right, so we're back to the keyboard here. So it's obviously a loop to check if the keyboard is responding or is present and ready to accept a command byte. And it's this JSR at the top jumps into that loop. So we want to look for 17180 now. No, come on, brain. It is obviously too late in the day. 17200. Yes. And that's doing memory map setup again. And we're decoding an instruction incorrectly there, I think. 16746. 67 is fetching the immediate, that's correct. 46. So decrements the value at our... no. Mode 4 is post-decrement. Pre-decrement. So it decrements R6 and fetches from there. Yeah, it's obviously doing a dereference that isn't getting caught by my inverse assembler there, so that's no good. So I'll have to restart the... I thought I'd set the flag that caused it to put a restart button at the top, but obviously I didn't. So what we want to do is 17226, start there. Right, let's see if there are any more with that bit pattern. Ah, hello Carrot House. Sorry, I didn't see you pop in there. Ah, I see you're already discussing getting bored of me and running off to Majenko's. Well, that's fine. It is coming up at the top of the hour. Maybe Majenko wants to go for the full... God knows how long this evening. We shall see. Hi, Spies. Well, sort of. We fitted a new DRAM chip to replace one that was dragging one of the address bits or address data bits down, but it hasn't allowed it to get any further into the boot as far as I can tell. So we're just trying to work out how far it is getting, but I have a bug in my inverse assembler which isn't helping. So we've got another one there. MOV, so 02 is MOV, isn't it? 02. Idiot. 016746. So it must be the... It's either 6... So the PDP-11 special cases... when you look at an instruction like this one, 016746, 01 means this is a move operation, which takes a source and a destination register, or source and destination operand, and an operand specifier on the PDP-11 is 3 bits of mode and 3 bits of register number. So 67 means R7, which is the program counter, in mode 6, which is indexed, which means that there is a word following the instruction which contains an offset to be added to the program counter to find the actual operand. But it special cases some things, and maybe my code isn't taking something into account. The destination operand here is 46, which is mode 4 on R6. Mode 4 is pre-decrement, which means the register R6 contains the address of the operand, subtract 2 from it, and then dereference it to find the operand. So what are we doing? We are doing the immediate fetch, which is correct. Because we don't have any visibility into the process's internal state, so we don't know what is in R6. But we do know what the offset is. So let's fire up the old calculator. I may not be daft enough to have a banned Python calculator routine, but I don't use Python as a calculator anyway. I use 342. 017 230 or 226, one or the other, close enough. And we subtract 27220. So, is it decoding? I'm just trying to work out which bit of the instruction it isn't correctly decoding at the moment. 017 230. So we can see it fetches the word following the instruction, which is 150560, which is, okay, so that's a signed number, so that's this minus 27220. It should then add that to the program counter to dereference something, and we are ending up at 170012. I get 170010, but that's close enough. Oh, of course, because it'll be 17232 will be the program counter by the time it's read that. So 27220 subtract 170012, so that's correct. So either I need to add a dereference for that, or I'm missing whoops. Okay, now you get to see the disassembler source code if I can find it. Where is it? OBS. Of course Visual Studio Code doesn't show up as being called Visual Studio Code, it's just code. That makes perfect sense, thank you. So if we turn that on, right. Live coding stream, people, this is what you wanted. This is what I definitely didn't want. So we want print operand PC. What are we special casing? 6.7, so mode 6 relative, print nothing, pull the immediate and so that should fetch his immediate. So what do we need to do there? We need to... We're not in a jump, so that's fine. Because jump doesn't actually dereference its argument. If you jump to a register that's incorrect, you can't do that because jump actually transfers control to the address of its operand, and because the registers don't have addresses, that's a trap. So yeah. DEC had some interesting ideas here, let's put it that way. But you must not speak ill of the PDP-11. So if bits 4 to 3... Bits 4 to 3 are going to be 1-0. 666. Where's the data sheet gone? Right, use of the PC as a general purpose register. Let me just... Oh, you can't see most of my Visual Studio window anyway, that's nice. So we're in mode 6. Relative address follows the instruction. Oh, relative address of operand. Right. Let's see if I can fix that. There we go, more code. That's what you want. So 4.3. So what's mode 2? Immediate operand follows instruction. So everything above 3. So modes 0, 1, 2. And then 3 does a defer, then 4, 5. We can return there, and we can return there. Let's give that a go. So over to DOSBox and recompile it. Moment. And oops, and put that back on controller mode. Oh, that's not a good sign. RS232 input error. Well, I think I might have just screwed the pooch. So while that chugs away on that, I'm going to catch up with chat for a moment. Yeah, Phil, it's well, we all know. Certainly, certain vintages of DRAM have a tendency to throw their little legs in the air. I was half hoping that dropping that new chip in this would fix it, but obviously we're not quite that lucky. While this chugs away, has that Amstrad monitor arrived yet? Because I forgot to reply to you on Freddy during the week, but I was pretty sure that the 1512 is hardwired to only produce a 200-line video output, and it's always RGBI. So the PCMM just does a weighted sum of the RGBI lines to get you a 200-line mono signal. You need the PCMD for a TTL for a video plus intensity. As far as I know, anyway, because that's what I've got on my 1640. But I'll be interested to hear how you get on. Let's just have a bit of a read here. Of course, what I need to do is fit a speaking of MDA style H-Sync V-Sync video and intensity, it looks like that's what the logic analyzer runs internally, so I should be able to fit a DE9 on the back, wired up as if it were a mono monitor, but I don't know what the signal timings are like. But if I feed that into an RGB to HDMI, maybe I can get better screen capture off it. Oh, I hadn't seen the intensity input. The black input is a bit of a mystery from what I can tell. It's not well documented anywhere. I don't know whether it's just some sort of output from the gate array to allow it to make sure black is always true black on the display, regardless of your contrast and brightness settings. Zen, thanks for the follow. Did that show up in the thingy with the alerts? Oh no, it probably didn't because it was hidden by the window capture. Sorry. I wonder if that file has downloaded successfully. No, the logic analyzer has crashed. Right. Okay. One moment. This is one of those fun serial issues. By default, the logic analyzer wants to speak X on, X off, so that you can use a 3-wire serial connection. I've tried that, and for whatever reason, my terminal software doesn't like it at all. when that's turned on, the analyzer just likes to beep and talk about RS-232 input errors, which is interesting. Oh no, I've forgotten what address we'd set the capture to. So you try RTS CTS instead, which the analyzer also supports, and that doesn't work because the VT240 chip is horrible. It doesn't properly implement hardware handshaking like that. Cypress have a pin-compatible one which does, which I built my first serial dongle around, and then hacked up some drivers for macOS to turn... Splendid. Hacked up some drivers to turn on the relevant handshaking bits when that dongle was connected. But then I managed to kill that dongle by using it to support a sort of, I think it was about a 20 kilogram modem or something, because IBM. That was a mistake. So I fitted the actual FTDI chip, thinking that at least the drivers for that are built into macOS, and it just doesn't work very well at all. So what I have to do instead is IO port configuration, controller on RS-232, no handshaking. So the crap printer type. What we have to do instead is send the file using just fairly crude delays in between packets, effectively, where the settings transmit 1 second delay after every 64 bytes. I mean, that's what I'd been using and it was working, so let's try it again. Connection send file. That's not right. RMDLT11 pin. Try that again. Send file. And hopefully this time it won't beep and moan at me about an RS-232 error. You can't see the progress message at the top, it just says storing file to disk, so... yeah, you can moan at me all you like, that's what I'm here for after all. I mean, yeah. I've probably just made a complete mess of my inverse assembler, so this stream might be coming to an abrupt end in a minute. We'll see whether this works or not. But if anybody happens to remember what instruction I'd set as the start of the trace previously, it would be grateful. Yeah, most appreciated in chat. It says storing file to disk still. Oh, okay, we're still going. Oh, I've forgotten to turn on the... There we go. Enjoy that for a while. I'll go and get a glass of water. Run a poll, how screwed is it? I think not is not an option here, but it's either incredibly screwed, very screwed, or unbelievably screwed. Right, that time it worked. It said it errored at me because it wasn't actually running in a state analyzer, but that's fine, that's as expected. So we should be able to reload the partial startup. And I can't read that message. Oh, operation complete. Useful, thank you. Right, so what we want to do is try and remember where we were. So JSR 16640 was where we left off last time. Or previously anyway, 16640. So that was the jump to that loop, and we wanted to try and excise that loop entirely, didn't we? So that was from 25350 through to we need to find the return. 25350. Don't tell me we're going to hit the end of the capture before we find we are indeed. Oh, hello T2 SDE and Raiders there. That's a new one. Thank you. And OXMLV, thank you for the follow. Yes, indeed. Ben goes. What I'm making at the moment, I'm making an absolute mess of things. That's what I'm making at the moment. I have one moment. Let me switch back to the main camera. I have a. If it'll come into focus, the innards of a DEC VT240 on my kitchen table, and this is a text and graphics terminal that I was given recently. It has been in a colleague's, effectively, garage, attic of an outbuilding for many years. And when I plugged it in and turned it on, it didn't work, so we're trying to figure out why. So far we have recapped the power supply, because that might be a nice easy thing, and it had a couple of reefers in it. It didn't come up. We found what might be a couple of bad gates on there, and we found a bad DRAM chip which I've replaced, and now we're trying to work out why it still isn't booting. So I am using my logic analyzer to trace through its boot process, instruction by instruction, to figure out what's going on. And so far the answer is not much. We've just returned from a break where I updated my inverse assembler, which is what's generating these instruction listings here, to cope with a incorrect value. And I've just realised I might be able to find that in my calculator history. 1 second. Exit that. No. Base octal. Sorry, bear with me one moment while I look up the instruction that was failing. 27220. And if we add that back on, 17232. Let's try resuming our search from there and see what happens. Whoops. 017232. Run. Well, that's not ideal. May have lost sync. Well, there's a... Aha! My InVasm button is back. Can you see that? Where's OBS? You cannot. There is now a button at the top of the screen there labelled InVasm, and what that does is it tells the inverse assembler to restart processing on the top line of the display, so we can bring it back into sync from that failure, and there we go. We're now decoding that instruction correctly. That 016446 is take the word following the instruction, which is 15560, treat it as an assigned offset from the current PC, which will be 17232, fetch the value that's there, and then decrement R6 and then write that value into the resulting address, which is here. So there's the fetch and there's a write. It should be doing a read, modify, write cycle there. Oh, it is. It's reading what is in 161146, which is what R6 now points to. It reads it, then updates it. So we're back on track there. Void Manger, hello. Oh, Void Main in Germany, I see, yes. Sharon AXP, I've never used Sharon AXP. I have actual alpha hardware in the office to run various versions of OpenMS. Excuse me one moment, please. Sorry about that. Yes, it was my father ringing about something. Yeah, so I've got actual VAX Alpha and Itanium hardware in the office for running VMS stuff on for work. This is just for nonsense, basically. And the VT240 is based around a DEC T11 PDP-11 on the chip microcontroller. Well, microcontroller effectively. Can I move it up a degree or two? Possibly. It's whether I nudge the camera behind it is the worry. Yeah, that's about as far as it goes, I'm afraid. Yeah, so this is a DEC T11 on a chip, which implements nearly all of the PDP-11 core instruction set. Doesn't have any floating point operations in it. More face, less beard. Yes, okay. Sorry about that. I hadn't noticed it was... Well, I'm sitting a bit too far back at the moment. But anyway. So let's get back to trundling through all of this. So what are we doing here? We are writing a whole bunch of stuff into R6. And R6 is... It's copying backwards into a buffer at 16114 something or other. Is that in the memory map? The memory map. No, it's outside of the I/O space. So where is it? I'll show you what I'm looking at. Secondary camera, Safari. There. So we're looking at 161146. Well, that's the top of ROM. That doesn't make any sense. 1644. Okay, so now we've hit another problem, I think. Either it's trying to write into ROM there, which is obviously not going to work, or it's set up the memory map so that address is no longer ROM. Unless I'm not miscounting digits, am I? No. Okay, let's assume it's writing that into RAM, which starts at 2, all the zeros. So we'll assume it's not being stupid. Whoops. And there we go, back to testing something at 170100, which is... Oh no, I've lost the symbol table I set up, but it wasn't working anyway, so 170100 is the command register. What is the command register? I shall turn Safari back on. NVR interrupt control command register, there we go. We're looking at bit 1 in the command register, which is either memory map on or T11 low. T11 low. Well, let's find out which way round it is first. Command register. There. Bit 0. D5 map on. So what it's doing there is checking that the memory map is turned on. Okay. You would have thought, well, it must be a subroutine, because otherwise you would have thought it would know it's just turned it on. And then we do 170040. Oh, I'll tell you what, is it? What does it do? Branch not equal plus 100, not taken. Loads. Where would plus 100 be? 17356. Okay, that's a lot further on. So move. No, that one. That one. You couldn't see what I was looking at then, could you? Okay. 170040. Memory map selection. Oh, sorry, Q4UX. Sorry, I missed your follow there a few minutes ago. Thank you for that. Oh no, I have blown nearly twice past my target for taking the live look at the DEC rainbow. I was hoping to get this machine working first so that we could use it as a test for an RGB to HDMI, so that I know I have good video capture before I fire up the rainbow. And also because the rainbow was stored literally underneath this. So yeah, this was sort of on top of the rainbow in the same attic. So if this is dead due to environmental factors, then maybe the rainbow is too. We should have to wait and see. But hopefully later in the month, my calendar's on the other side of the door. Hopefully end of the month we'll take a look at the rainbow, and in the meantime we'll look at the RGB to HDMI. But for the time being, let's try trundling through this list a bit more and seeing if we can find a spot where it's going into a loop. What I'm actually interested in is, does it get as far as looking at the NVR, which stores the configuration data? Because when it fails, the keyboard lights read 5 if they're read left to right, which is 0101, so that's 10 if you read it the other way around, and there are unfortunately not very many documented error codes in the manual. Let's see if I can find them. Problem solving. Yes, the manual says in the self-test mode during power on, the monitor screen and the keyboard indicators provide information about the terminal operating status. The monitor screen displays a text message while that's not running, and the keyboard indicators provide a coded message. It doesn't give you any way of decoding that. There is no documented error code 5. It sits in between error code 4, serial port cannot operate, and error code 6, keyboard can only receive input from the host. But 10, if we read the bits backwards, 10 is non-volatile RAM error. The NVR setup storage is not available. So let's look to see if it's getting as far as accessing NVR, which is at 176 anything. So if we go back here and set that to 176, don't care, don't care, don't care. And we don't care whether it's a read or write either. Let's run that, see what happens. Put that line at the top of the screen and resync. Okay, we appear now to be stuck in a infinite loop, which is a good sign. No, we weren't stuck in an infinite loop. But we never got as far as touching NVRAM. Now let's go down to the end. Oh, now that's interesting. Why are we executing code from address 1? That's the boot vector. Well, address 0 is the boot vector, but you can't run from an old address on the PDP-11. Yeah, there's definitely something wrong there. We're just running the first 2 instructions of the boot process over and over. Jump to 137, swap a byte in memory, swap 2 bytes in memory. So there's a word addressed by R0, which is at 177640. Swap the 2 bytes around there, and it's doing that incorrectly as well. Because it's reading 137777, so there is a clear bit. Bit 14 is clear in that, and it's writing back all 1s. So maybe that's the problem. Maybe we now have an issue with a stuck bit at 13 is definitely bit 14, isn't it? So let's bring up the oscilloscope and have a quick look. and I can't reach any of that because the logic analyzer probe's in the way. One moment. So we want a oscilloscope probe, and we want to probe. Hang on. Where's the schematic gone? And we want to probe bit 14, which will be on E11, which we know about, pin 14 or pin 2. So that'll be this one up here. Well, that wasn't particularly conclusive. Well, that was definitely some weird stuff going on there. Pin 2. I do have a dump of the ROM, yes. I need to obviously run it through a disassembler and see what's going on. We can do that bit right now, actually. Hang on. Well, we can check those first two words. That's not a problem. Where is Hex Fiend? Sorry, one moment, and open file. Where did I put the ROMs? I have the ROMs here somewhere. Downloads. VT240, here we go, VT240 reference interleave ROM. And we are looking for let's switch this back to hex, make it easier to find it in the dump. So 005F at the first, oops, yep, 005F is correct, and then at hang on. Hang on, my brain is shutting down here. Turn on the inverse assembler again. 137, immediate fetch. No, that something doesn't make sense there. if we ignore the low bit, because it can only run code from word-aligned addresses, .137 is correct. It's a jump to an immediate, but then it fetches 137 from the same address and jumps to... That makes no sense. What's the correct startup? Let me bring in... Sorry, if I bring in... I think that's the right one. Let's make it a bit bigger. So there's the the 137. We'll switch back to hex, and it's easier to correlate the two. Let's move that so you can still see. And then that's where it should be jumping to 1D6E. Right, so it's obviously getting caught in the weeds at some point. So what we want to do is trap on the first read from instruction 1, or from address 1, because it should never get there because it can't run code from an odd numbered address. So we set that to 1. And we set it to a fetch like that, and we'll run that. And this time we didn't actually seem to get there, so it could just be spurious as the thing shuts down. Yeah, okay, I think that's just because I turned the machine off at that point. Right, so Majenko, if you want to warm up your stream, I think we've probably reached the end of where I can go with this off the top of my head today. Not bad, it's 45 minutes over usual time. Yeah, so the next steps will obviously be to run this through an actual disassembler, so I can try and follow where these various loops are. And if we can follow the startup through the code itself, then we'll have a better idea of where we can set breakpoints on the analyzer to work out what's not happening, which should be happening. I presume that Discord notification was you going live, Majenko. So yeah. Disappointing progress. I was hoping we would have made a lot more progress with that today. We corrected a bug in the inverse assembler, that at least is good, but we haven't brought the thing back to life, which is bad. So I'll crack on, and then we'll think about doing the RGB to HDMI next week. I know I said that last week, but there's only so much staring at a logic analyzer screen full of nonsense that chat can take, I imagine. So yeah, thanks for joining me, everybody, and we'll hop on over to Majenko's and see what he's doing. Well, it's sort of assembly. What it is the logic analyzer is capturing the data that's flowing on the CPU's memory bus, and usually it would just show you raw machine code like that. And last week we worked through the first few instructions to verify what they were doing, and you do that by hand by looking at sort of opcode chart like this one, and working out what everything is doing that way. But you get fed up with that, so you can write what's called an inverse assembler, and what that does is it looks at each individual word and tries to decode it. So rather than disassembling the entire program, it's looking at one word at a time, trying to work out what's going on. And that is this one, which is decoding it to, let's roll that up to the top of the screen. So that then gives us assembly code derived from the data that's going past. So like I said, we need to run the entire ROM through a disassembler and try and figure out what the actual code path should be and where we're deviating from that. But yeah, thank you for joining me, everyone. Sorry we didn't make more progress than that, and this has probably been a bit dull, but I shall hopefully see some of you next week.